So, fortunately for me, a lot of the points I wanted to make initially have been made by the previous speakers this week. So, so that's going to make my job easier. So, I want to. I'm still at heart a programming language person. So, I think of my endeavors in formalization as programming math, and I'm going to use some of my favorite examples to illustrate the topic. So here's my mantra. The main issue I've encountered or dealt with during formalization is that if you just look at a normal math article or textbook, the actual formal contents, definition of the theorems, don't state their intended use. They don't explain how they're going to be used, and in order to have a workable formalization, you have to capture that intent to some extent. One particular, especially egregious instance of this is that mathematical notation is concise on purpose for efficiency, because if you start cluttering your text with all sorts of irrelevant details that can be figured out by any knowledgeable reader, you won't get to your point. And so it's essentially ambiguous. Overloading is probably the easiest part of it. But in essence, the notation that needs to be used if you actually want to practice mathematics can't possibly make sense logically if you take it at face value. Another instance of this, which I'll illustrate, is the fact that mathematicians love to use patterns of proofs that do not side well with the formal prover's notion of proof. This disappears if you don't want to prove stuff, but the notation problem doesn't. And in order to make formalization relevant or even feasible, you have to address these topics to some extent. You can't do just nothing. My belief is that you can call programming and computer science to the rescue. To deal with the proof part, in principle, you can do things by just programming proof generation tactics, and that's been done for forever, I think. It's been more recently that systems have tried a bit harder to crack the math notation nut. So it's been finally realized that there's this elaboration phase where you need to mediate between what a reasonable user wants to type and what a reasonable logical system needs to see in order to make sense of what's been written. And it's possible, and Lean does a fairly good job of it, to do a lot of this elaboration, again by tactics, by programming the surface engine. But the more rewarding way of doing this is to actually program the mathematics. So realize that there's actually mathematical knowledge in explaining how the notation maps to ground concepts. So, so here's my favorite toolbox for doing this. So the first tool is data types, or types, or proposition and proposition types. So my point is that types are the essential linchpin of doing this, capturing the subtext. Essentially, a type is the intent that's written behind the surface or the object meaning of some text, some object description, or some proposition statement you're writing. So the type is saying what you the notion between object and type is the notion between text and subtext. And you can have it in a hard type system and you can have it in a soft type system, but all practical proof developments, even systems that are completely untyped, have some kind of type system put on top of it. And it's better if the type rules are set and the tools help you with the type rules. But even if you're even in cases where you don't have that, you still want to put types, and even in cases where you have type rules and they don't suit your meaning, you put in your own separate type system on top of the on top of the existing one. And yes, you need to do this even if you have a very expressive dependent type system with all sorts of features like cock or lead. So my second favorite tool is to have computation inside types and inside values, inside types, because that makes programming possible. And in many cases, it's much easier to just write the code that does that makes sure that your text just evaluates to what you mean, as opposed to trying to add rules that say that it has to be interpreted to some simpler meaning. And I don't know why this is speeding forward. So dependent types are a useful feature because they let you have basically first-class structures. So it's and structures are basically what you need to have to be able to talk about types themselves and to do this kind of meta reasoning. What makes all of this usable is the fact that you have elaboration that infers types and infers missing type information, infers missing values even. And in Cog, this is controlled by coercion, canonical declarations, type class declarations, and you've seen examples of this, and you'll see more later on. And the final piece, which I'm not going to talk a lot about, which also it's important, is user notation. This is usually just the entry point into. I view this as essentially not the layer that does all the elaboration work, but just the thing that gives you a foothold, and you try to get the more elaboration you can do inside the logic, the better you generally are, because the more you understand your the internal subtext of the math you're doing. So quick recap about canonical structures, though I guess you were exposed to them in Cyril's talk yesterday. So the idea is just the standard one of using records to group mathematical objects. And the approach of canonical structures is not to try to mess around with having parts of things and parameters and parts of things separately. So when you want to quantify over a field, you need to have at least 2, if not 15 parameters. The thing that makes this palatable is to use unification to fetch the appropriate record based on the operations you require. And the nice thing about this is that it interfaces very directly with the elaboration at a very low level, at the level where basically in every sub-expression, if you need something, then you will trigger this kind of inference. And the kind of type class inference that's done in Coq it tends to be a little more removed from the problem, in that all the unification will be done, and then elaboration will kick in and try to fill in the missing pieces. But by that time, it may be too late to figure out what the expression meant. in principle, you can combine both approaches. I tend not to do that, but. This is my canonical example of why these things is useful. So that's actually the definition of trace in the MathComp library. So this is what you type. If you remove the surface level, this is what the elaboration engine sees with lots of missing information to be filled in. This is what unification initially fills in. Just based on usual Hindley-Milner type inference, and then the canonical structure stuff figures out actually what ring you're working on, or rather what additive group you need based on the fact that you're in a ring, and then how to enumerate the index range. And this thing has mathematical meaning. The top thing with all the missing holes doesn't. And you really don't want to be typing in the thing in the bottom. And you really want to be able to have the flexibility of just writing the thing on the top and have all the missing pieces filled in, and not have to pre-fill the thing by putting yourself in a specific context, because the minute you want to play around and have 3 kinds of matrices with different coefficients in different fields, you're going to have to mess around with multiple contexts. Here, the structures are being inferred as you need them, and you don't need to do a lot of proof planning and put yourself in the right context in order to have things work properly. So all this interfacing requires having all of these structures, so basic ones that do equality, and then ones that give you the operations, and one that give you the properties of the operations. And you have lots of canonical structures. The fact that you're working with unification gives you a lot of flexibility for defining your data, something that I'll probably go quickly because Stephen talked about this at length yesterday. So the fact is that you can have little basic blocks that are mix-ins, and then the traditional historical way of doing nested structure would have you nest these things like matryoshkas, which is bad because it's basically forcing the representation to reflect the hierarchy structure, and the minute you have diamonds, you realize you don't want to do this. And so what you can do instead is just put everything on a flat level, and then just use computation, very small amount of computation, to just pick out pieces and reconstruct the records on the fly. And your evaluation will make sure that everything comes out nicely, and you don't have these diamond problems of having the same thing being constructed in 2 different incompatible ways. So you can do more than have structures over types. You can have structures that give properties and even data based on other data. So here's one example that's really useful if you're doing algebra, a structure that tells you whether a given function, a given map is linear. So that's the basic form of it. But if you start working a little more with these things, you realize that this is not enough. And you want to have something a little more general where this is
something. keyboard working?
No, I'll do it. I'll do it this way. Both you might have you might need to twist the scalar when you take it out of the linear function. So you have something like, the technical term is sesquilinear. So the typical case is if you have linearity over complex numbers, you might want to take conjugates as you move out. And the other thing you might have is a consequence of the standard ambiguity of the mathematical notation, which believes that, which will just write juxtaposition for any kind of product, and have these wildly ambiguous things where you can either multiply things inside the same type or multiply things that are of completely different types. So you can have inner and outer product. And linearity actually is a concept that's useful for both things. And so it's nice to have both things be mapped to the same thing. So you can have something like, for example, polynomial evaluation actually be recognized as a linear function. In this case, so if you combine evaluation with mapping a ring morphism over the coefficients, that is actually a general linear function. And you want to do more than that. You'd actually write this rule to be able to match this rule both left to right, where you're going to pick out the morphism sigma, the ring morphism sigma, and the multiplication operation, whether it's internal or external, from the structure data. But you'd also like to be able to match it the right to left. Because half the time you want when you want to use the equation, you're using it in the other direction, and you can do that too. You just need to use a few more structures. I've been bantering about the benefits of using having a fancy type system and using dependent types. One of my early experiences with formalization in working with the four-color theorem was to a place where I discovered that you could actually overdo this. And there are places, even if you have a fancy type system, doesn't mean you always have to use it. So the place where I went wrong was when I wanted to, I needed to actually formalize the concept of paths, because I was doing graph theory and running around maps trying to color them. So I had picked up the traditional Koch manual, and it said, oh yes, you want to do a dependent type family to describe paths. That's how you're, that's the proper way of doing things. And this is terrible. You might want to do something a little lighter and have just a dependent type. And this is bad because Koch basically, the logic actually interprets this as a generalized form of equality. So it wants to rewrite, if you want to use this thing, what Koch wants to do is rewrite your entire goal. And this is generally not what you want to do. So you can do things a little better in having just the type where you have the additional property of having satisfying the whatever graph relation you have at every step, and that's kind of nice. And I developed about half of the theory for the four-color theorem using this, and then hit a complete roadblock because I realized that I had this formalism where I had the same base set of points and different graphs superposed on top of it, and I wanted to be able to say that I have the same path. That's a path for different relations, and this is terrible with this because your data embodies has the intent that that you're a path for a specific relation, and so you have to translate. I had to translate paths from one representation to the other all the time. Ultimately, the simpler thing was the thing to do. What you had to do was just make the trail explicit. Just say, oh, it's just a list, and then you just have a property that says you're a path. And then you can, when you want to combine paths, you can just use the list operations and everything will work fine. So that was my first exposure to the fact that subtypes are really an interesting concept, and you should use them when it's appropriate. So the next place I encountered this was when we started working on the over theorem, and I needed to work with lots of groups, and then I quickly discovered that what you're doing all the time is saying that you have the same element and it's in two different groups at the same time. So if you start saying groups are types, you're in hot water because you just can't write that. Groups are not types. Group theory is really a misnomer. It's really should be called subgroup theory. So you can do things try to do things in the light way and saying, okay, I'll have this basic types of finite sets, and then I'll have the soft type for groups. You can actually do something better than that, because you can use a structure to infer the property of this group, this subgroup closure property automatically. And that turns out to be a huge win. So you're having groups as subset means that your theory is a lot simpler than it used to be, because a number of places where you have to put annotations in standard math or use something, use a special symbol to say that you're a subgroup as opposed to just using inclusion. Having to talk about the normalizer inside a particular group as opposed to just the normalizer in the entire type over which the operation is defined. Life just becomes a lot simpler. And you can even get rid of, you can even generalize the notion so that you also cover multiplication of subsets. You don't need a separate theory for group sets. And if you apply this strategy to quotients, then you discover what was mentioned earlier in an earlier talk, that cosets and the first isomorphism theorem has actually data in it, and so you can define things with this based on this data. And if you do this, you realize that, okay, you're actually going to define the morphism, and then the definition of a quotient is just the image under that specific canonical morphism. And the nice thing about this is that this extends the notion of quotient to something that is a god-awful expression if you have to write it down in standard group theory notation. But the fact is that, at least for the text I was formalizing, this expression shows up all the time. And so somehow, or rather, for a wrong reason, there's been this insistence that you should only be able to write this as G/H in a special case where H is a normal subgroup of G. Turns out the reason for this is that you have the third isomorphism theorem, which says you can simplify group fractions, and you are only allowed to simplify the group fractions if you have normal subgroups. And so this is the same precaution as the precaution against dividing by zero. There's nothing wrong with dividing by zero and giving a default value for division by zero. It's just that simplifying by zero is really, really bad. And if you have a proof checker behind you, you don't need to have this particular safety mechanism around that is polluting your notation everywhere. You can simply rely on the theorem prover to tell you, well, no, you can't use a third isomorphism here because it's not a normal it's not a normal subgroup.
So, do you have a counterexample in mind where you cannot do this simplification?
Yeah, if you think about what the third isomorphism is, it just doesn't work. Well, if you actually need the assumption in order to prove the theorem.
Because in your other expression, H is even just an arbitrary subset, right?
Subset.
Yeah. Yes. So that occurs less often that you have to take the generated subgroup of the subset, but it does happen. Because if you look attentively, the definition normalizes uses H, the group generated by H, to generate the cosets, but it restricts to the actual normalizer of the set H. So there's this. These things are more subtle than you think. So this was probably our first true litmus test of this approach of doing group theory, so proving the CELO theorems, and it gives you nice notation to state the theorems, and it gives you a fairly nice proof of a theorem where you basically follow the math proof, and you're not okay. So this uses the level of automation of Koch, not that of Lean or Isabelle. So you have little paragraphs, little technical paragraphs between the statements, but roughly it's a fairly straightforward proof, and the proof is literally 10 times the size of what it used to be before there was the mechanism for inferring the group properties.
10 times the size, you said?
I'm smaller.
Yeah, it was 10 times larger. So adding the mechanism, the Gonthier had written those first proofs, and so when I checked in the updated proofs, he actually went in and looked at the Koch terms to see where all his work had gone, and realized that yeah, it was still there in the actual proof term. It's just been generated by the logic itself. So one more example of this about characters. So this is my cheat sheet for characters, but hopefully for this audience, you only need to recall that characters are traces of matrix representation of groups. And the important thing is that characters are invariant under group conjugation, which is the equivalent in group theory of changing basis. So the basis is dependent. And they form a Hermitian space, hence the need for sesquilinear functions. So based on my experience with, SOAR experience with paths and groups, my first instinct was to say, oh, yeah, okay, characters are, I'll need to use soft typing. I don't really want to have a type of characters, I want to have a type of something that's a little more general. So I'll just use the type of finite functions from group elements to complex numbers, or algebraic complex numbers in this case. And then character will just be a predicate, and I'll just use soft typing. And then I can define the Hermitian product in the usual way. And that's actually fairly close to the mathematical notation, but it's actually fairly inconvenient because you can't just talk about the dot product and talk about orthogonal things. You always have to specify for which group you're taking this product. So there's useful data associated that you're not getting. And a little experiment, and you have to carry out these class function assumptions all over the place. And a little experimenting made me realize that actually there actually is a data type associated with class function. If I took the entire textbook on character theory and realized that the author never mixes class functions over different groups. This never happens. So now putting types to good use, you can create a real type for class functions, and then define characters as a soft type over class functions. And now your life is a lot easier because, for instance, you can talk about the Hermitian space structure without having to worry about saying which structure you're looking at. It all makes your life easier.
So I didn't get that. So when you say the dot product don't use G, you mean because
no, the dot product uses G, but the G is in the type now. So therefore, you don't have to specify it because your type carries intent.
Like G is not an explicit parameter of the dot product.
It's not. Well, it's an explicit parameter, but it's inferred. It's carried out by the type.
So what it means the notations don't use G.
The notation doesn't need to use G because G is in the.
Okay, so
unified
you
from
can
the
make it an
class
implicit parameter. I don't know if it's.
Yes.
So you can even do more with this notation stuff and give meaning to things that are really meaningless on the surface. So in math, you'll see statements like this. This sum is direct if and only if the ranks the corresponding rank sum are equal. And actually, we can write this. We can define these extended structures in order to be able to write this in Coq. So this is a statement that's completely generic in the form of the sum, and it's used. It can even be used transparently if you have a definition that will mean the proper. It will have the correct meaning. So you can really push the envelope, and this is a lifesaver if you're doing spectral theory. So obviously, this is talking about eigenvalues, but if you, it especially meshes nicely with a little facility for handling convex inequalities. So just having a three-way predicate saying m is less than n, and if they're equal, then some other condition will hold. Because you can have this statement that basically is the equivalent statement for matrices, and then you can use this in development, and at some point just invoke this statement and get you get from something fairly trivial, which is an arithmetic equality, you get something extremely strong, which is a direct sum statement, which lets you create having a unique decomposition. So this is how this code executes, and the magical part is here, where you get all of a sudden you get all sorts of properties. So this is an example where this code is just inline because it's a small chain, probably in the one of the longest proofs in the entire Over theorem proof, is one which has this particular step where there's this whole set of properties you are going to prove, and this is going to be proven by having this long chain of circular chain of inequalities. Now, Koch doesn't yet have a calc mode, and of course, I assume that Lean's calc mode doesn't handle three conditional inequalities either. But you can sort of fudge it by having lots of intermediate definitions. So here are all of the terms that are going to be involved in inequalities. Then you just show each of the steps of the inequalities, and having definitions means you don't need to repeat the sub-expressions all over the place. And then you have this magical step at the bottom when you've basically used transitivity to collect all of the conditions, realize that you now have an equality, and then you just extract. At that point, you know that all of the condition holds, and then you extract all of the content of the conditions. I don't really like to have a calc mode that does this, obviously.
But I don't understand what this is doing. So there are side conditions to your inequalities?
Yeah. Typically, you have
side condition to the
you have a statement that says this inequality holds all the time, and if equality holds, then this additional condition will hold.
Okay.
So it's a typical convex. This happens typically with convex stuff. So one of the cases where this will happen is with direct sums of the if you have an inequality over ranks or dimensions of spaces.
Mm-hmm. So this notation, so less or equal and then question mark equal if and only if, it means the LB0 is less than LB1, and with equality if and only if the...
Yeah, exactly.
Okay.
And the transitivity does
and the transitivity will collect the conditions.
Okay. Yeah, so that would be a nice exercise in writing elaborator doing that. Okay, nice.
So the GI1Q, DAP that appeared in the bottom line, all the statements that you see appearing in the F.
You basically extract all of the statements, and this is kind of the last line of that lemma, because the statements appeared explicitly in the term. And I had another bit about proof automation, but since I'm running out of time, and this is a bit secondary to my topic, though I have a vested interest in looking at the proof. So computation is nice. Gives you a nice way of proving things if your intent is proving things by using an algorithm. So having been able to write the algorithm inside your proof language and running it is nice, and you can run the algorithm entirely inside the proof checker and have it do the proof. You can run algorithms that do parts of the proof, and I guess this is something that's very much done in Lean now. And so yeah. And so I did this mostly for the four-color theorem, but it actually turns out that in proving the over theorem, there's an instance of this where there's a combinatorial problem, and the combinatorial problem looks very simple, but it's complicated enough that if you just try to brute force it with SMT or whatever, it just fails. You could sort of tailor and restrict the problem so that the SMT will solve, but it's much more satisfying to actually look at the original proof and realize that this proof is written in a specific proof language, and you can implement that language inside Coq with very little code. Okay, so summing up, there's a lot of implicit content in math. If you want to do formalization, you have to cope with these conventions, especially notation conventions, diligently. Programming language tools are pretty much up to the task. There's lots of room for improvement. However, I think the source point is probably that in order to do this properly, right now, because we just have basic programming tools in the system, you need to have the specialty skills of programming language stuff, programming interpreters, programming term traversals, whatever. And giving feedback to lay mathematicians, saying, look, this is what your notation really meant, and this is how to interpret it. You just you don't really have a nice language to say that. You can point at things like I did with the quotient or the class function type, but really, the details can be quite gory, and I'm not sure how I would get them across. So elaboration should clearly do more, and Cyril has done great strides in that. And I'd really like to have more natural notation as well, and perhaps will be saved by ChatGPT. And I guess we can debate this afternoon.
Yeah, there will be the panel discussion. So thanks, George.